All right, when we're looking at double integrals, we're looking at, something like this, some function of x and y integrated dA over some rectangle, all right? And the rectangle in the xy plane is, between a and b for the x's and between c and d for the y's, all right? This is the rectangle R. Um, every once in a while, you get a really special case, and that the function of x and y can actually be written this way. So this is not always, this is only sometimes, right? That the thing that you're integrating is actually some function of x times some other function of y, right? That it can be written as a product of two functions, one just as a function of x, one just as a function of y, okay? In that case, what you can do is the following. That Fubini says you can set this up as an iterated integral, either dx dy or dy dx. So this is g of y, and it doesn't really matter. Let's say dx dy. So the x is going from a to b, and the y is going from c to d. Okay? But look what happens here. That the inside integral here is with respect to x. Well, g of y is just a constant with respect to x. So you're multiplying by that constant. Well, heck, you can just pull that right outside the integral. And it looks like this. You've got the integral, you've got the integral from c to d of g of y. Boy, my g's and my y's look a lot the same, don't they? G of y times the integral from a to b of f of x dx dy. So do that inside integral, multiply by g of y, and then multiply by dy. Well, when you do this inside integral, you're going to find an antiderivative. You're going to plug the b in, you're going to plug the a in, and you're going to subtract. And that's now going to be just a number. Well, you're multiplying that number times this function and then integrating. Well, one of the properties of integrals is you can pull that number out in front. So you've got the integral from a to b of f of x dx. That's just a constant with respect to the variable y. And then you're going to now do the integral from c to d of g of y dy. The net result is, if this is a function, if your function is a product of two, just of x and just of y, and you're integrating over a rectangular region, then you can pull it apart this way. Now, so far all we've done is rectangular regions, but when we get to 15.3, we'll do some non-rectangular regions, and you can't do this. But in the event that you are doing a rectangular region, well, then you can just pull it apart. So for instance, here's an integral. Let me do an example here, e.g., for example, how about the integral of x squared sine y dy dx integrated from, let's see, x is on the outside, from 0 to 7, and we'll integrate y from 0 to pi or something like that, okay? X squared times sine y, that's a product of two functions, just of x and just of y. Okay? This is a rectangular region, and so I can split this up. I can say, all right, this is just the integral from 0 to 7 of x squared dx, and then I'm going to multiply that by the integral from 0 to pi of sine y dy. Each of those are easy enough to do. So this is x cubed over 3, evaluated between 0 and 7. And then I'm going to multiply that by, what do I got, negative cosine y, evaluated between 0 and pi. So, well, whatever this is. This is 7 cubed over 3 minus 0 times negative cosine pi minus cosine pi. I think that's 2. All right, so I've got 2/3 times 7 cubed, whatever that is. There you go. It only works if you've got a rectangle that you're integrating over, and the function that you're integrating is a product of just x's with a function of just y. Just x's times just y's. Anyway, it'll save you some time every once in a while. There you go.